In section 2.6, we're going to look at combining functions. We are first going to look at combining functions using arithmetic. So we're going to add them, subtract them, multiply them, and divide them. The other way that we're going to combine functions is forming composite functions. So after studying this section, you should be able to find the domain of a function, combine functions using the algebra of functions, so adding them, subtracting them, multiplying them, and dividing them, and we need to specify the domain after we've combined them. You should be able to form composite functions, and when you form composite functions, determine the domain for those composite functions. Finding a function's domain. If a function f does not model data or verbal conditions, its domain is the largest set of real numbers for which the value of f of x is a real number. Now, sometimes your data limits the domain of your function. One of the early examples we looked at in this chapter was someone taking their temperature after they woke up feeling ill. So they started taking their temperature at 8 a.m. and they called that time equals 0. So the domain of that function is restricted by when this person started taking their temperature. So the domain would have been x is greater than or equal to 0. In interval notation, we would say from 0 to infinity. Now I understand that someone taking their temperature, they're not going to do it forever. So there probably is an upper limit to this domain also. But the data is what limits the domain of that function. However, if we're given our function in terms of an equation, how do we determine the domain of that function? Well, what you're going to do is you're going to exclude from a function's domain real numbers that cause division by 0 and real numbers that result in an even root, such as a square root of a negative number. Okay, so those are the two things we're going to look at when we are given a function defined by an equation. Are there real numbers that I can substitute in for my input that would cause division by 0? If there are, I must exclude them from the domain because division by 0 is undefined. I also must exclude any real numbers when substituted in for the input would cause the square root or the fourth root or the sixth root, any even root of a negative. We know that the even root of a negative number is imaginary, and we're going to restrict the domain of a function over the set of real numbers. So we're not going to have a domain that contains imaginary numbers. Let's do some examples. So I have the function here, g of x equals 5x over x squared minus 49. So I have a function being defined using an equation. And in this case, I have a function where I have an input variable, x, in the denominator of a fraction. The denominator of this function is x squared minus 49. So are there values that I can replace for x that would cause that denominator to equal 0? And the answer is yes. There are two numbers that if I plugged them in for x, I would get 0 in the denominator. And that would be 7 and negative 7. But if I just can't look at that and determine what the domain is, how do I figure out what the domain is? Well, what I do is I take the denominator and I set it equal to 0. Because then I'm going to be able to find the values of x that would cause that denominator to equal 0. And those are the values I'm going to exclude from my domain. My domain cannot contain the number 7. It cannot contain the number -7. Let's show you how this works. So you set the denominator equal to 0. This is going to give me the restrictions on my domain. All right, so I'm going to set x squared minus 49 equal to 0. That's a quadratic equation. So we studied those earlier in chapter 1. So how do I solve a quadratic equation? You have 3 different methods that you can use to solve a quadratic equation. You could factor this. It is factorable. You could use the square root property. That works very well for this type of quadratic equation because it has no term that contains an x. And we could use a quadratic formula if we were so inclined. I'm going to use the square root property because it works very well for this. To use the square root property, I'm going to add 49 to both sides. Then I'm going to take the square root of both sides, and I'm going to get x is plus or minus. Remember, when I take the square root of both sides, I must put the plus or minus in front of my constant on the right-hand side. And what's the square root of 49? Well, the square root of 49 is 7. 7 times 7 is 49. So I get x is plus or minus 7. So those are the 2 numbers that would cause my denominator to equal 0. So x cannot be -7. X cannot be +7. Because if I put in -7 for x, I would get a 0 denominator. If I put 7 in for x, I would get a 0 denominator. All right, so how do I write this in interval notation? Well, I think the easiest way to see how to write it in interval notation is to draw a quick graph of this. So I have my number line, and I have a hole at -7. X cannot equal -7. I also have a hole at +7. X cannot equal +7. But anything else on the number line is okay. Any other number on the number line except -7 and +7 will be appropriate inputs into this function. So how do I write this? Well, the first interval I'm going to write are all the numbers to the left of -7. If you are to the left of 7, you are less than -7. So that interval is from -infinity to -7. Now you'll notice I'm using a parenthesis next to the -7 because I need to exclude that from the domain. The second interval over which the domain is defined is from -7 to +7. So any number between -7 and +7, excluding -7 and +7, would be okay. I can certainly plug 0 into that function, no problem whatsoever. I can plug in -1, I can plug in 2, any number between -7 and 7 is okay. So in interval notation, that is the interval from -7 to 7. Again, you'll notice that I'm using parentheses next to the -7 and 7 because I have to exclude those from the domain. The last interval is all the numbers to the right of 7, all the numbers greater than 7. And how do I write that in interval notation? The numbers to the right of a number, I write that as 7 to infinity. And then I can join those using a union symbol because it's the interval from -infinity to -7, or from -7 to 7, or from 7 to infinity. The domain of this function is defined in any of those 3 intervals. The only 2 places the domain of this function is not defined is at -7 and +7. So if you have a function that has a fraction in it and it has variables in the denominator of that fraction, you just need to check, are there any values that if I plug those in for x would cause that denominator to be 0? If they exist, if there are numbers that you would plug in and you get 0 for the denominator, you must exclude those from the domain. How about this example? What did I do here? The only thing I did here from the previous example is I changed this to x squared plus 49. All right, now are there values that I could plug in for x and get 0 for the denominator? And the answer is no, there isn't. Because any real number that I square, and that's the first part of this denominator, x squared, any real number I square is going to be positive. So this right here will always be a positive number, always. There is no real number you can square and get a negative. Well, what happens when I take a positive number and I add 49 to it? It's still positive. So there is no restriction on the domain of this function. I can input any real number that I want. So the domain is a set of all real numbers, which we denote as negative infinity to positive infinity. All right, so what if you didn't recognize that? What if you didn't notice that when I square x, I get a positive number and I add 49 to it, it would be positive. So the denominator will always be a positive number. What if you didn't notice that? Well, you could use the same procedure we used on the previous example. Set the denominator equal to 0. And again, I'm going to use the square root property to solve this. So I'm going to subtract 49 from both sides. I get x squared equals negative 49. I'm going to take the square root of both sides. And so on the right-hand side, I have plus or minus the square root of negative 49. Well, what's the square root of negative 49? As you recall from section 1.4, if I have the square root of a negative, that is I times the square root of that number. So if I have the square root of negative 49, sorry about that, that is I times the square root of 49, which is plus or minus I times 7, which is plus or minus 7i. Okay, that's not a real number. Neither one of those are real numbers. Those are both imaginary numbers. I have 7i and negative 7i. Those are not real. So there are no real numbers that will satisfy the equation x squared plus 49 equals 0. Since there are no real numbers that satisfy that equation, there are no real numbers that will make the denominator of this function equal to 0. So since there are no real numbers that will make the denominator equal to 0, the domain of this function is the set of all real numbers. All right, so what if you have a square root? I have the function f of x equals the square root of 3x plus 12. Well, I would have to exclude any values for x that would cause that radicand. Remember, the stuff underneath the square root symbol is called the radicand. So let's highlight that. That is called the radicand. If I'm in real numbers, that radicand must be non-negative. And what do we mean by a number being non-negative? Well, if I draw a number line, what numbers are non-negative? Well, the numbers to the left of 0 are negative. So the numbers to the right, including 0, are non-negative. So if I drew an arrow to the right of 0, but I put a solid dot at 0, because 0 is also non-negative. So negative numbers are to the left of 0. non-negative numbers are greater than or equal to 0, or to the right of 0, including 0. So with all that being said, how do I figure out what the domain of this thing is? You're going to take your radicand and you're going to set it greater than or equal to 0. So to find the domain of a function that contains an even root, so a square root, a fourth root, a sixth root, etc., the radicand of that root may not be negative. It cannot be negative. It must be non-negative. So you take the radicand and you set it greater than or equal to 0. So you take the radicand, whatever it is, and you set it greater than or equal to 0. Okay, so in our case, we have 3x plus 12 is greater than or equal to 0. The radicand must be non-negative, and this is a linear inequality. You can solve that using the rules for solving a linear inequality. I'm going to subtract 12 from both sides. I'm going to divide both sides by 3, and I get x is greater than or equal to -4. So how do I write that in interval notation? Well, that would be all the numbers to the right of -4, including -4. So to the right, we start at the number and we go to infinity. So this would be the set from -4 to infinity. And that makes sense. It makes sense that if you were to substitute a number smaller than -4 into that function, for example, if you evaluated it at -5, let's say, that's a number smaller than -4, what happens? Well, we would get the square root of -3. And that is not a real number. So -5 must not be in the domain of this thing. So the domain must be numbers greater than or equal to -4, because any number that I substitute into this function that's greater than or equal to -4 will cause an output that's in the set of real numbers. So we'll be fine as long as it's greater than or equal to -4. Okay, how about this one? And this is similar to the problem that we had a minute ago, where we had a square in the denominator of a fraction. So is there any real number that will cause that radicand to be negative? And the answer is no. Because what happens when I square a real number? Every time I square a real number, the result is positive. You cannot square a real number and get a negative number. It can't be done. So when I square x, that's positive. When I multiply it by 3, that's positive. When I add 12, that's positive. So this radicand will always be positive. So since it's going to be positive for any x, the domain is the set of all real numbers. And I should be able to write that correctly. From -infinity to positive infinity. Okay, so how can we combine functions? Let's first look at the algebra function. We can combine functions by using addition, subtraction, multiplication, and division by performing the operations with the algebraic expressions that appear on the right-hand side of the equation. So the sum function, f plus g of x, we just add the two functions together. So f plus g of x, the sum function, we add f of x and g of x together. The difference function, f minus g of x, we just subtract the functions. So we subtract g of x from f of x. Now the problem with the difference function is that we make sign errors. We forget that we're going to distribute that negative across everything on the inside of parentheses. So just be aware of that and be careful that when you're subtracting an algebraic expression from another algebraic expression, you distribute the negative across everything on the inside of parentheses. The product function, you just multiply the two functions together. So fg of x is f of x times g of x, and you're going to use the distributive law or FOILing to find that product. And then the difference quotient, you're going to take f of x and divide it by g of x. And this is the one you have to be careful with, because this is the one where you can introduce restrictions on your domain. So in our case, the two functions that they're using is f of x equals 2x and g of x equals x minus 1. So when I write the ratio of those two functions, f of x over g of x, I now have x minus 1 in the denominator of a fraction. And so x can't equal 1. So the last one, the quotient function, we have to be careful with that and make sure that the domain of our quotient function is properly defined. So we want to make sure we exclude anything that would either cause 0 in the denominator, or with all of these, we would have to restrict the domain if we had the square root. All right? So here are our 4 functions that we can create using addition, subtraction, multiplication, and different quotient, division. I'll spit it out. So with the sum function, to find the sum function, you add the two functions together. The difference, you subtract the two functions. The product, you multiply them. And the quotient, you divide them. Okay, so given two functions, let's find the sum, the difference, the product, and the quotient functions. All right, let's first find the sum function. To find the sum function, f plus g of x. So that is the notation that we use for the sum function. In parentheses, we have f plus g, and then we have of x. F plus g of x is f of x plus g of x. And we just add those two together. And I can put those in parentheses just to show you that that first stuff inside parentheses is f of x, and the stuff in the second set of parentheses is g of x, and I'm going to add those together. Now, they're only to show you that those are two distinct functions. There's no number on the outside of those parentheses except 1, so I can just drop them. So what do we get? And I'm going to combine like terms and rearrange things a little bit. So there is my sum function, f plus g of x. And now let's talk about the domain. So the function that we obtained when we added these two functions together was x squared plus x minus 6. That function does not have x's in its denominator. It does not have an even root with an x in the radicand. So the domain of this function is the set of all real numbers. There is no value I cannot substitute in for x. Everything works. So its domain is the set of all real numbers. All right, let's find the difference function. To find the difference function, and the notation we use is f minus g of x, I'm going to subtract g of x from f of x. And I need to be careful when I do this to make sure that I subtract all of g of x. So when I distribute that negative across, I want to be sure to distribute it across both terms inside those parentheses. So I get x minus 5 minus x squared plus 1. minus 1 times x squared is minus x squared. Minus 1 times minus 1 is positive 1. So now let's do a little bit of rearranging here. Negative x squared plus x minus 4. So my difference function is minus x squared plus x minus 4. And let's talk about the domain of that function. Again, it's quadratic. It's a quadratic function. And we talked about that in section 2.5. And a quadratic function, its domain will be the set of all real numbers. So the domain, in this instance too, is the set of all real numbers. There's nothing I can't plug in. Oh, I didn't write that very neat. There's nothing I can't plug in for x. I can plug in anything I want. Let me write that a little bit neater. All right. Now let's see if we can't find the product and the quotient function. So let's find the product. And we denote that as f times g of x. And we're going to multiply the two functions together. All right. So I'm going to multiply this by foiling it. So I have first x times x squared is x to the third. Then I'm going to do outside x times negative 1 is negative x. And I'm going to do inside negative 5 times x squared is minus 5x squared. And then last, minus 5 times minus 1 would give me plus 5. And I'm just going to rearrange this a little bit to put it in descending order of power, descending exponents. All right, so now looking at this, what's the domain of this function? Well, this function does not contain a square root. It doesn't contain a fraction with an x in the denominator. So the domain of this function is the set of all real numbers. There's nothing I cannot plug in for x. I can substitute any real number in for x. All right? So the last function we're going to find is the quotient function, which we denote as f over g of x. And to find it, we divide the two functions. And I noted up here, just now I looked up, I didn't write the formula for the product. You multiply the two functions together. Make sure we get that on the slide. All right, so now I'm just going to write the ratio of x minus 5 over x squared minus 1. So now I am going to have a restriction on my domain because there are values I can substitute in for x in this function that would cause the denominator to be equal to 0. And I could just look at that and probably figure out that if I plug in 1, that's going to be a problem. If I plug in negative 1, that's going to be a problem. But I can set this denominator equal to 0 and solve it and then determine what those two restrictions are. So let's do that over here. So we're going to set our denominator equal to 0. I'm going to use the square root property. So x would be plus or minus the square root of 1, which is plus or minus 1. So those are the restrictions on my domain. X cannot equal negative 1 and x cannot equal positive 1. And I think you can look at that. If you take negative 1 and you plug that in, negative 1 squared is 1, 1 minus 1 is 0. I can't do that. If I plugged in 1, 1 squared is 1, 1 minus 1 is 0. So how do I write that in interval notation? Remember, on my number line, it would be everything but negative 1 and 1. So the way we write that is from negative infinity to negative 1, union with from negative 1 to 1, union with from 1 to infinity. Okay, so those are our 4 algebra functions, functions that we can add together using arithmetic, or we can create using arithmetic. You can add functions together to get a sum function. You can subtract functions to get a difference function. You can multiply them together to get the product function, and you can divide them to get a quotient function. All right, the other way that we can combine functions is by combining them using a composite. All right, so to understand this new type of combination, let's look at this example. So suppose you go to your local computer store and they're having a sale, and they've got 2 different sales going on. The models that are on sale cost either $300 less than the regular price or 85% of the regular price. So one model you can get for $300 off, and maybe another model or 2 they're going to sell you at 85% of the original cost. So let's write the 2 functions that represents these 2 sales. So the first function we're going to call f of x, and that function is the original price of the computer minus 300. So the input x is the original cost of the computer, and the function f of x represents the sale price. So f of x is x minus 300. So if your computer originally cost $1,500, you would get it on sale for $1,200. So if your input is $1,500, your output, the sale price, would be $1,200. The second function represents paying 85% of the original cost. So again, the input is the original cost of the computer, and the output would be the sale price. So g of x we could write as 0.85x. So if you had a $1,000 computer, the input would be $1,000, the sale price would be $850. Okay, so let's say you're a savvy bargainer and you bargain with the salesperson, and she finally gives you an offer that you can't refuse. She says she's going to give you both sales. So she's going to give you 85% of the regular price, and she's going to reduce that cost by $300. So she takes the price of the computer, and you're going to get that price, 85% of that price, and then you're going to subtract off from that $300. This sounds like a bargain to me. All right, so what you're effectively doing is taking that function f of x equals x minus 300, and you're replacing x in that function with the other sale price, the g of x, 0.85x. So you're taking f of x and replacing the input of the function f with the output of function g, 0.85x. So now the cost of your computer is 0.85x minus 300. So again, if it's a $1,000 computer, you pay $850 minus 300, so you'd pay $550 for that computer. So this is how we compose 2 functions together using the composite. So the function g was 0.85x. So the input of g was x, and its output was 0.85x. And we took this output of g and we made it the input of f. And that's exactly what a composite function does. We took the output of g of x, and we made it the input of f. So we took the output of g and made it the input of f. And that's a composite function. When you take the output of one function and make it the input of another, that's a composite function. So f of g of x is the 0.85x minus 300. We call this the composition of the function f with g. The composite function is written f open dot g. So whenever you see this notation here, That means the composition of the function f with the function g. So f, the composition of the function f with the function g of x is f at g of x, or take the output of g and make it the input of f. And sometimes I abbreviate this and I read it as f composed with g of x, which is the notation we have at the bottom of this slide. F composed with g of x means to take the output of the function g and make it the input of the function f. Okay, so now suppose the original price of your computer was $1,400. So f composed with g of x is 0.85x minus 300. So you replace the x with 1,400. So f composed with g of 1,400 is 0.85 times 1,400 minus 300, which would be $890. So this means that a computer that regularly sold for $1,400 is on sale for $890. Okay, so in this slide just shows you how this works. The original sale was, one of the original sales was that you're going to get 85% of the original cost. So it's going to cost you 85% of the original cost. So if the input of the function g was 1,200, its output is 1,020. So a $1,200 computer would cost you $1,020 if all you got was the 85% of the original price. But if you take that output of g, the $1,020, and make it the input of f, now you're going to subtract $300 from that output, and that would give you $720. So here's the definition of the composite function. The composition of functions. The composition of the function f with g is denoted by f dot g, and is defined by the equation f composed with g of x is f evaluated at the output g of x. So f composed with g of x is f at g of x. Now, the domain can be kind of tricky on composite functions, so you have to be careful. The domain of the composite function f composed with g is the set of all x such that, first of all, x has to be in the domain of g. Since g is the function that we're going to get the output from, any value of x that is not in the domain of g must be excluded. You have to exclude it. And the second criteria is that g of x has to be in the domain of f, because g becomes the input of f. So g of x, since it's an input of f, must be in the domain of f. Since g of x is an input, all inputs must be in the domain of function. Okay, so here is an image that represents what we're doing when we compose two functions. So let's say I have a function g. The input of function g is x. Therefore, x must be in the domain of g. And then I'm going to output some g of x from the function g. And then I'm going to take that output g of x and I'm going to input it into the function f. So g of x, whatever it is, has to be in the domain of f. It can't be an input of a function if it's not in its domain. Inputs must be in the domain of the function. Okay, so let's look at an example of finding a composite function. So let's find f composed with g of x. So by definition, f composed with g of x is the function f evaluated at g of x. So in my function f, wherever there's an x, I'm going to replace that with g of x. So this is going to be 5 times g of x plus 6. So I replaced the x in my function f with the output of g, which is g of x. Well, but what's g of x equal to? Well, g of x is equal to what? 2x squared minus x minus 1. So I've replaced the input of f with the output of g. The output of g is 2x squared minus x minus 1. And then I'm just going to simplify this. I'm going to distribute the 10 across, the 5 across. I'm going to distribute the 5 across. I had my brain on. 5 times 2 was 10. So I distributed the 5 across. 5 times 2 is 10. 5 times negative x is negative 5x. 5 times negative 1 is negative 5 plus 6. Let's just combine like terms. So there is f composed with g of x. All right, so let's talk about domain. Okay, so if we look at g of x, x must be in the domain of g of x. Well, the domain of g of x is the set of all real numbers. There is no restriction on x when we're looking at g of x. There's no square roots, there's no fractions there that contain an x. So the domain of g of x is the set of all real numbers. So if it's in the domain of the composite, it must be in the domain of g. Okay, now let's look at g of x outputs. So g of x is only going to output real numbers. It's not going to output anything else. It's not going to output imaginary numbers or anything like that. So g of x must, its input must be able to be put into f of x. So whatever output we get here, we have to be able to put that in f of x. And that f of x, its domain is also the set of all real numbers. F of x is a line. It's a linear function. So there is no restriction on the output of g of x that I can't put into f, excuse me. So there's no output of g of x that I can't input into f. So the domain of the composite function is the set of all real numbers. And you probably could have just looked at that and determined that that was true, because if you look at the composite function, it's quadratic, and the quadratic function's domain is the set of all real numbers. So there's nothing I can't input into that composite function. So the domain of the composite function is the set of all real numbers. All right. All right. Again, the following values must be excluded from the input x in the composite function. If x is not in the domain of g, it cannot be in the domain of the composite function. And any x for which g of x is not in the domain of f must not be in the domain of the composite. Let's look at an example. Okay, so I have f of x equals 4 over x plus 2, and I have g of x equals 1 over x. Let's find the composite function, and let's look at the restrictions on the domain of this composite function. So first of all, just looking at g, let's just look at g. G of x has a restriction on its domain. X cannot equal 0, because if I let x equal 0, the denominator of this fraction is 0. So it has a restriction. X cannot equal to 0. So 0 cannot be in the domain of the composite function. If it's not in the domain of g, it cannot be in the domain of the composite function. All right, so now let's form the composite function. F composed with g of x is f evaluated at g of x. So wherever there's an x in f of x, I'm going to replace it with g. Okay, now let's pause. 4 over g of x plus 2 is the composite function. Now I'm going to simplify this in a minute, and I'm going to replace g of x with 1 over x, and then I have a complex fraction that I need to simplify. But I need to pause here and look at the domain of this thing. Okay, I cannot let the denominator of this fraction equal to 0. That's not going to be in the domain. So fractions denominators cannot be 0 because that's undefined. So g of x plus 2 cannot equal 0. If g of x plus 2 is equal to 0, then I got 0 in the denominator. I can't do that. So g of x cannot equal negative 2 if I subtract 2 from both sides. Well, what's g of x equal to? Well, g of x is 1 over x. So 1 over x cannot equal negative 2. And if I solve this equation, I can cross multiply. I have x cannot equal negative 1/2. So those are the two restrictions on my domain. X cannot equal 0, and x cannot equal negative 1/2. So let's recap. I have two functions, f of x equals 4 over x plus 2, and g of x equals 1 over x. And I want to find the composite function f composed with g of x. Okay, first I need to look at g of x. G of x is equal to 1 over x. If the input is not in the function g, it cannot be in the composite function. So if there's any restrictions on g, then it's going to be a restriction on the composite function. And g of x equals 1 over x, x cannot equal 0. If x is equal to 0, then I have 0 in the denominator of fraction. That's undefined. So the restriction on g is x cannot equal 0. So that will be a restriction on my composite function. X cannot equal 0. All right, then we compose the function. F composed with g of x is f at g of x. So in my function f, I'm going to replace the x with g of x. So now I have 4 over g of x plus 2. G of x plus 2 cannot equal 0. So 1 over x cannot equal, g of x cannot equal negative 2. So 1 over x cannot equal negative 2. So x cannot equal negative 1/2. So here are the two restrictions on my domain for the composite. X cannot equal 0, and x cannot equal negative 1/2. And then we'll write that in interval notation on the next slide. All right, so let's go ahead and finish the composite. So I do need to do a little simplification. So I had 4 over g of x plus 2. But g of x is 1 over x plus 2. And you can simplify this any way that you have learned to simplify fractions of this type. I would probably rewrite this and maybe get a common denominator. So that would be x, so it'd be 1 over x plus 2 times x over x. Okay, and to divide, we multiply by the reciprocal. So I have 4 times the reciprocal of 1 plus 2x over x. So I have 4 times x over 1 plus 2x. So I have 4x over 1 plus 2x. So there is the composite function. And that's the way I would simplify it if it were me. So that's the way I did it. All right, so now what's our restriction? Our restriction is that x can't equal -1/2 and x can't equal 0. So maybe I'll graph that up here. So I have holes at -1/2 and 0. Everything else is okay. So my domain would be from the -infinity to -1/2. Union from -1/2 to 0, and from 0 to infinity. Get that erased. Let me write that in a little bit better place so that we can see it. Writing it down there is kind of hard to see. Let's write it up here. So we have from -infinity to -1/2. Union with from -1/2 to 0. Union with from 0 to infinity. And that is the end of section 2.6.